Log on, tune in, find out. Another good idea from Cambridge.
Okay, so thank you very much, Frank, for the invitation. I will call on the Log-Concave Ensemble. This is based on the work, on joint work with Radek Adamczak, Alexander Litvak, and Nicole Tomczak, Yegeman. And I will survey the last two papers recently on the Log-Concave Ensemble. So the word ensemble here has to be understood in the sense of random matrices. It means a set of matrices with some probability structure. So the setup of this talk will be the following. We will consider a random vector x in Rn with the following two properties. X is isotropic, which means that it is center and that the covariance matrix is the identity. So this denotes the Euclidean norm for all theta. And the second, x is log-concave, which means that the distribution has a log-concave density. So this will be the setup of this talk. In fact, the results are more general than this situation, but this is to fix the setup. So essentially, if you want to have a basis example is the basic example here to have in mind is x is uniformly distributed on a convex body. So this is a basic example that we have in mind. So x, the body is isotropic means, of course, exactly what is written here. So the covariance matrix is the identity. So we will now look at the sample. So the vector x is our prototype, and we look at a sample of size n, which, as you will see, in practice, essentially will be larger than n. And we look at the matrix x1, x2 with these columns. So it is a n times n matrix. So it's a random matrix. And we will introduce immediately an object, the image of the cross polytope by the matrix A. So the cross polytope is the unit ball of L1, and the image, of course, is the symmetric convex hull of the vector of the columns. So first thing to notice, what are the faces of the cross polytope? Of course, how do you find them? Very easily. So let subset I of 1 up to n take a choice of sign with these indices, then the convex rule of this is a face of dimension, of course, with H and Xi as vertices. So this is the most complete structure of a symmetric, centrally symmetric polytope, because you have all the possible faces that you can imagine. They are obtained by choosing a sign and choosing a subset of cardinality, of this cardinality. So we will analyze how the matrix transfer this property.
So here it's with xi or
You are right, I am already transferring. Where EI is the canonical basis of Rn. So you understood the next line, which is the definition of so let's call these polytopes, let's give it a name, P. The polytope P is M neighborly if the image by A, so PA is the image by A of the cross polytope, if the image by A of every K faces, K face of B1n is a face of P. Whenever K is less than n minus 1. So a K face is a face of dimension K. So all the faces are simplices. And here I am studying only the case of centrally symmetric, which is more delicate than the case of non-centrally symmetric neighborly polytope, where you transfer the image of the simplex. But this is they are very well known of how to construct such neighborly polytopes. And as you will see, there is no known way to construct centrally symmetric. So in the literature, they call it, this is called an centrally symmetric neighborly polytope. Okay. I also, for this lecture, I will suppose this, you see, if I suppose here that the vertices of P, say V, is a set of plus x1. This is to simplify. So I suppose this you see, M neighborly for M equals 1, in fact, is empty statement. Because M neighborly means that if you take M point, less than M point, they are of the vertices, they are the vertices, exactly the vertices of a face. Okay. So M equals 1 means nothing. So here, in fact, implicitly, I will suppose that these are vertices. If not, then this is, of course, it means that you are taking subset of V. So the first question I will study here is the following: how neighborly can the polytope P can be? So this is the first question, which is a question which was beginning to be studied long time ago, and where essentially the first answer were found only recently. So The first case, which was the first and important case which was studied, is when x, so this is x is our prototype, x is a Gaussian vector. So it's very, so in the sense of this example that I told you to have in mind, so it means x is a random point in the Euclidean ball, corresponds to this. Or x is on a random point uniformly distributed on the sphere. So this has been studied by David Donohoe. And it was a great result of David Donohoe to show that m can be on the order of n log n over n. So it means that with high probability, so this is the way one has to understand this sentence, with high probability, whatever it means here, then a random polytope P, which is defined by a Gaussian matrix or a random point on the sphere, is m neighborly with m quite large. From this work, there have been a lot of work, so there are many names which are were involved in this work for other cases than Gaussian. Was the work of Candes and Tao, and then the works of Lignal and Novik, and the work with Charles Mandelson and Nicole Tomczak-Hegeman, where we were studying in particular 0-1 polytopes coming from vertices of the cube. The results are always the same. So the result I want to show you is the first result which was proved in the general context where the columns are have not independent entries. So the following theorem, which is from the fourth author I recall on this blackboard, is say the following things. Let n to be less than this number, and I wrote it somewhere, maybe, that it was larger than n, little n. Then, with high probability, in fact, this is the best possible estimate. Probability is larger than something like exponential minus square root of n. Then, P is m neighborly, centrally symmetric, of course, m neighborly, whenever with m on this order of n divided by log square, or put a constant here to avoid maybe n to be equals n. So this is the result I want to discuss, the first result I want to discuss. And in fact, the result is quite strong. I will not write the complete statement. It tells you that not only all P transfer, the matrix A transferred the low-dimensional face of the cross polytope, but it preserves also all the metric structure. So each time you take a face, it is far from the convex rule of all other with the same distance. So there is the complete structure of the low-dimensional face are preserved. So it's a kind of universal statement. Up to this level, it doesn't depend on the convex body. After some level, it is clear that it will depend if you take too many points. But I will discuss later about the optimality of this expression here. So how to handle this? Well, we come back to the work of David Donohoe. So Donohoe proved the following nice equivalence, which will be the key here. P is m neighborly. So I recall that in this definition, I suppose that it means also in neighborly, I put that all the points here are vertices. if and only if, whenever the system AZ y equal AZ as an n-sparse solution, it is the unique minimizer of the following program of the that I will call LP, minimize the L1 norm, maybe I'll put only one bar, of AZ under the constraint of AT So this is the, in fact, this is this is not a difficult statement, but this is a very important relation. So something is missing. I will maybe P is n-ably. If whenever you look at a system like this, which has an n-sparse solution, the n is the m, then this solution is a unique solution of the linear programming problem, which is
Norm of T or of
sorry.
norm of T?
You're right. That's totally right. This is the L1 minimization problem. So once you know this, it's quite an exercise to find it. Okay? No, Bella, it's not clear.
What's the minimum of what?
So you minimize over Rn. So this, if the system has an m-path solution, and this you know, then you will find it by minimizing the L1 norm over this constraint. So of course, all the people who have been in the talk of Candace or yesterday in the talk of Avi Vigderson know that this is of course the L1 minimization problem in compressed sensing, and this is the link between neighborliness and the problem of compressed sensing, which was discovered by David Donoho. So it's an equivalence. Now, how to handle this problem of compressed sensing? There was a series of talks, so I will not discuss it again. So I think many people here probably were at one of the talks of Candace or the talk of Avi. So anyway, I will not enter the subject of compressed sensing. I will use it as a tool here to continue. So to analyze the structure of the faces here, you have to look at this problem. Here, this is just a deterministic statement. There is no randomness. If you have a polytope P and the matrix A, which is associated, then you have to try to see how far can be M such that you have always a unique solution. So you already heard about the restricted isometry property. So I will repeat this definition. So let gamma be an n times A matrix. So A gamma satisfies, if I'm going to query, because I'm supposing that some people here heard the talk, there was a series of talks of Candace and yesterday the talk of Avi. Gamma satisfies the RIP of order M with constancy. Delta, if gamma is almost is an isometric embedding on the sparse vector. So let me write it like this. Where UM is the set of norm 1 vector in Rn so that the support of X is M is supposed to be small, though this is why I call it sparse. In fact, it will not be so small because it is of this size. Okay, but this is the definition of sparsity. So usually, of course, this is written in the form that, but let me write it like this. Okay, so this is an almost isometric embedding of UM in L2. Yeah. In L2 little dimension N. So this always, I don't put the European number. So I change the notation of the matrix gamma because you have to normalize it. You see, you should start from the matrix A and look to vector X. Of course, yes, the vector is like this. So if you take the expectation here, you will come up, because of independence, to this. But because the isotropicity here hypothesis tells you that the covariance is the identity, then this is the sum of on the coordinates, so this is little n. So it is little n. So the matrix gamma will be the matrix A divided by square root of n. This is the natural thing that we have to look, and we are looking to such an inequality to be to satisfy the RIP property. So here, this is the natural normalization here. The one here, of course, we could have changed. The one is, of course, the expectation of this vector, and this is behind a kind of concentration inequality. So, why is this property RIP very important? It is, and Emmanuel Condes recall it. Maybe I should now erase something here. It is because it is extremely difficult on a given matrix A to check this property which is equivalent to M Nibelines. So the RIP is a tool which is a sufficient condition to show that it will imply this. So the main theorem, which is due to Condes and tau, and the estimate I will give here is due to Condes, tell you the following thing. So I apply it to my matrix, which is at rescale. If this is less than square root of 2 minus 1, then every m sparse vector Z is the unique solution of the linear program problem that I. So, if you can show that the constant here of the RIP property is small enough, then you can reconstruct every m sparse vector by the L1 minimization method, and then you have neighborliness. So this is the scheme of the analysis, which is already here in the work of Donohoe. So I put Emmanuel Condes here because in the first work there were other constants, and in fact square root of 2 minus 1 is not the best constant. It has been improved and improved. There are a series of papers. And in the Gaussian case, there are many asymptotics about the best constant. I will not discuss this. This is more a question of compressed sensing talk. So this is the objective now. The plan is clear. It's small, whatever means small here, some constant. And we will not take care of constant. So first observation, to understand in which direction we are going, look at the RIP property of order 1 before looking to RIP property to order n. So if you look to the property of order 1, then delta 1 of the matrix here is the sup over, well, you take only one sparse vector of norm. What is the image? This is a sup. So even at the beginning, when you look at this and you want this to be quite small, less than epsilon, then of course for people working in asymptotic geometric analysis, they recognize a problem of what is called concentration in a thin shell. So it gives immediately in which kind of in which pool you are working. Of course, you want much more than this, but at least to have the level 1, you need to have some concentration. And it is very why concentration? Because you see, there are capital N independent copies of this. So it means that if you take 1, the probability here must be very small. Have in mind n equals exponential square root of n. So it is really a concentration is in shell, okay? Because of the independence, and this is the sup which must be small, not only each individual. So this question goes back to a lot of work which has been done in this direction. So the concentration in the sheet chain asks, in fact, what is it? The starting question was the following: does there exist a decreasing sequence to 0 such that the probability yes, is say less than something like this. So this is the weakest form of the concentration in sheet shell, which was a question which was asked at the end of the 90s by Kisbo. And there was a lot of work which was done beginning by Antila, Ball, and Pirisinaki. And then huge work was done to solve this question, which was solved by Kartak. So it's something, I think I put the date somewhere. This is in 2007 or 6, the publication 7, and independently Fleury, Guédon, and Paris. So the question about this is very important here, because you see, in fact, very small means essentially that we would like to have something like this, because we want n of this order. So it is, in fact, very important to quantify this. And so there have been a lot of work by Klartag, by Fleury, and in fact the work which is the best work up to date now is due to Emmanuel Milman. So I put the E, there was a question yesterday about V. This one is Emmanuel Milman and Olivier Guédon. So it's, I don't know, it will not be published before, probably. So it's 2010, say. And it tells you the following. So, is larger than actual delta since the beginning, the constant of isometry here. is less than exponential minus c times square root of n. And here is the power delta, which is 3. The question about this power is very important, in fact, but it's not important in this work, because I told you, at the end, delta is a fixed constant. It's not going to 0 here. So the dependence in delta, which is very important in the problem of the concentration in a shell, the conjecture would be power 1. So this is a conjecture, but on which many people were working. But I should tell you that there is a recent result of Eldon and Clartag that show that it implies, if true, the slicing conjecture. So, but as I told you, surprisingly, it is not important here to have the right power. What Emmanuel Milman and Olivier Guédon and Emmanuel Milman got is this square root of n, which was not before. Before was some power, I forgot, 1/3, 1/6, I forgot, was improved by Fleury, etc. And it is important for our statement, which is, where is it certain? Maybe I erase it. But as I told you, even for delta 1, you want exponential square root of n, because then you will not go here. This, I didn't want to enter all the technical details. This ensures you that all the points are vertices. So, this was the first question I wanted to discuss. No questions? Okay, I have a question. Because I forgot, I say that I will comment about the difference between the Gaussian case and the general case. In fact, we don't know. We know that the result on RIP, that where did I put it, is optimal, but we don't know that it is true for neighborly polytope, because it is a necessary condition, not a sufficient. This is a sufficient condition. So this is the question that we don't know, and there are many cases where we know it is. There is, of course, you don't need it. For instance, when you have some symmetries, etc. But in general, we don't know, because we go through this property of RIP, and it comes naturally with it. This is optimal. The second question I want to discuss.
I have a question, huh?
Yes?
If you know the vector is psi2, you have the 1?
Yes, you have the 1, yes. There are many cases where you know that you don't need the power 2. So for instance, this was the case also for random point vertices of the cube, etc. You don't, this is really up the log square. The log is optimal. So the second question I wanted to discuss is apparently very different. How many points? So how large should be n? Do you need, are needed to approximate the covariance matrix. Up to epsilon by the empirical covariance matrix. Of course, with high probability. So how many points do you need to sample so that you can reconstruct the covariance matrix from the empirical? So I will write exactly what it means. But here, the setup is that the covariance matrix is the identity. But of course, if it was not, you can make a linear transformation so that it comes here, and it doesn't change the question of the number of points. So you may suppose always that the covariance matrix is the identity, and you're asking how many points do you need, and so what is the mathematical formula which expresses this? What should be n, so that if you sample the soup over the sphere is less than epsilon. Why? Because it is exactly, look, this is exactly the quadratic form which is defined by the empirical covariance matrix. So in some sense, the empirical covariance matrix is, if I write it in a matrix form, and now this is the operator norm that you want to be less than epsilon. These are the same questions. The problem looks very different because for the moment there is no sparsity which is involved, and this is, but as you will see, there is a very important link between the different questions. So this question also has a long history, which go back to a question of Cannon, Harvey Cannon, Leslie Lovas, and Shimonovich, which was a question of complexity of computing volume. I don't want to go back to this. So it's something which is from '96. So there is a first answer, which is in this paper, which is C. So I will not. There are two questions: fixed epsilon. How many points do you need? What is the size of n? So then there is a question of the dependence in epsilon. But forget about it. So here I should write C epsilon times n squared. Whatever is this dependence here. So this was immediately improved on the same a few months later when they asked the question by n log cube by Bourgain, so it's the same date. Then was a lot of work. The first important work was by Marco Delson, so this is 99. And this is of the same order. But the method of Marco Delson is very interesting, and there's a lot of influence even in compressed sensing. This is the selection method of Marco Delson. So it's a method of empirical processes. And then there was a lot of work by Olivier Guédon, Marco Delson, Yiannopoulos, Artsoulaki. I will not all quote. I will quote the main breakthrough, which was Gregoris Pauris in 2006, which give the n log n. And for some moment it was, because it was stuck, some people tried to show that something was needed here, but in 2006, the same year, Guillaume Aubrin proved that under unconditionality, which means that the density is symmetric with respect to all coordinates, n is of the order of n. And I should say here just that there are three methods here. So here it's a quite natural method because you are working with matrices. So you want a kind of uniform law of large number, and you are working in dimension n square. So you expect n square. So the breakthrough here is very important because you are working in matrices of dimension n square again. So here are three methods which are based on, all the methods from here to and all intermediate are Rudelson method, and Guillaume Aubrin was pure combinatorial. It's combinatorics on random matrices taking big power, trace, etc. So it's a pure combinatorics of a random matrix. So the answer to the question was in 2008 by the four authors, and the answer is that n is always, with high probability, proportional to n. So what I want to show you is today is the last improvement, which you will not maybe is not important to answer the problem of Cannon, Novas, and Shimonovitz, but this is n divided by epsilon square, same as in the Gaussian case. It is a little unexpected that it is even in epsilon like the Gaussian case. This is the best possible. So this is the best possible, and I will write the theorem exactly and try to show you now why the two problems that we were discussing are related to the same question. And it will answer, in some sense, how do you prove each of them.
Your method is different from the first three?
So the method will come back to method of Bourgain. So this is the point here. It seems that the method here of Mark Rudelson is introduced some distortion. So the theorem is the following, and I will write, you will see, just as a very simple statement. So you are interested in this expression here, the difference between the empirical quadratic form and the one, because this is the covariance matrix is the identity. So the probability that this is less than c times square root of n is larger. So it's a very clean statement. This is the end. So now you understand that if you want this to be epsilon, then you have n to be on the order of c at n divided by epsilon square. And you have this with the best probability possible. So it's a complete clean statement, which is exactly what you have up to the constant c here and to the constants which are involved. This is exactly the Gaussian statement. Sorry? Theta? Yes? Okay, thank you. So let me just indicate this, the proof, and then this is where we will see the link between the two statements. So proof. You want to have a statement here which is a uniform law of large number. So you start by discretization. So there is little n. You began to discretize as usual, just because you will apply, and you start to use a kind of epsilon net argument. So, no mystery, discretize and take lambda and epsilon net, say just to fix things at 1/2 net of cardinality. Probably you have to adapt constant of with cardinality less than constant to the well, say exponential Cn. So now you're looking. So this is there is no mystery here. So you're looking to soup over x theta in some finite set of this. So it is now individually a question of law of large number. So when you want the scheme to prove a law of large number is always the same. Is always the same. You truncate. So the second step is truncation. So this is the first step. The second step is truncation. So for the moment, everything is completely standard. What does it mean? It means that there is no probabilistic inequality in general if you don't have information. The only information is that the L2 norm is 1, and you need something else. Okay? You need something else here. And in particular, for specialists here, this, when the Gaussian case, so the square becomes sub-exponential, psi 1 as we say. So there are inequalities. But if not, if you take the exponential distribution, everything breaks down. You have inequalities, but they are not good enough. They are not good enough to handle so many points. So what you do is truncate. When you truncate, you have a good inequality, which is Bernstein inequality. So if you replace you truncate at some level, which will be a parameter now, B. It's random variable, and you apply the Bernstein inequality that I will not write. It tell you that if you take if you take a sample of independent random variable which have L2 norm bounded, L infinity norm bounded, you have a good inequality. And for this, you can handle, and I don't want to compute, I just want to see the plan. So after the truncation, you have to handle, now, you have to work with the rest. Is it English word, this? What's the rest of the rest of it? The rest is precisely with something like this. Usually, there is a kind of methodology. Usually, you prove it for an epsilon net, and then you use ellipsis. You compute the ellipsis constant, but it doesn't work because the ellipsis constant is too big. So there is a trick, and the trick is the starting point is due to Bourgain. The trick is the following thing. Notice that for the moment we didn't see the link between the two problems. It will come. So trick, there cannot be too many i's so that is big. So the problem is to compute how many. And then to work with, this is why there cannot be too many. The reason is the following. If you look For the rest, we don't care about concentration. Concentration comes from the truncated part, and then we have to control the rest by an upper bound. So we try to control this where it is big. But let me introduce a notation. Let EB to be the set of indices so that this is big. So it depends on theta. So when we are summing on this index, we are in fact summing on EB. Okay? So this is, maybe I should, because this is, I don't make any computation, so this is 1 up to n of where this is big. This is the same thing. But of course, this is larger than how many there are, and b squared. B is the parameter that will be estimate in an optimal way, I hope, at the end. So, to control this number, you want to control this expression. But you don't know this set. So it's a kind, first you should be very careful that this is a random integer, and second, you don't know. This is an implicit equation. So you will, so the second force set estimate the soup over the sphere. The fact that you discretize is not important here, of the sum of the square you will try, fix a k, to estimate this number. K, of course, will take the different value you will express here, and you will get something to maximize the cardinality. But you see, because you don't know this, you must prove an inequality for all k and valid with high probability for k equal 1 up to n. So this is the last point here. This is to estimate this. Once you estimate this, and this is in fact the key point of the paper here of Radek Adamczak, Sasha Livak, and Nicole and myself, to work with this inequality and to find the right estimate. Okay, so I will not compute this. So you estimate this, and I want just to tell you how it is linked now with the first problem. Where is involved the sparsity? The sparsity is naturally involved because this is another way of telling that there is not too many indices here. So, in fact, what you are trying to control, you start with your norm, with your matrix A. You start with your matrix A. You take a subset I of cardinality less than k. Here is k. I should have put m. And what you are trying to compute is the norm of this matrix. So you are trying to compute the norm of this matrix and over all subset I. And then over all k. So forget about this k. If it was little m, then it is immediately related to the RIP property. Instead, the RIP property in some sense is stronger because you want to more over the concentration. So for instance, if you prove this, then you will control the norm of all these matrices, all block matrices. So this is the relation between the two problems. So if you control all the blocks here, then you have a certain function here, b squared k, which is less than something that you solve. then you have the cardinality K. You got that indeed there are not too many i's, and so that you can plug it in the computation. So this is the scheme, and just I don't want to enter the proof. So all the proof consists in estimating this parameter here, and the same way to estimate the RIP property. So just to understand, this is where in fact the work begins, because the hard work is here because there are too many. There are too many with respect to the concentration. So you cannot use a kind of usual epsilon net argument. So you have to break things in small blocks on which you can use, and then you try to find a kind of optimal chaining. So this is the point here. I will not, but this is where is the technical part, in fact, here to estimate this parameter. And just to finish, I want to ask a few questions, because there are many things which were if you look at this statement, you may look at it in a different way here. So in fact here, what is the norm of this, what is this number here? So let be the eigenvalues we normalize it always. So this is A star divided by N. And of course, this is the maximum here, this number, which I call delta, well, it was delta N now. Well, call it, I don't know, this number, call it, this number M is the maximum between lambda N, what is it? Maybe we say something wrong. Lambda N minus 1 and 1 minus lambda 1, something like this. This is the operator norm. So the eigenvalues are not positive, and you have to reorganize them. So this is why you can, for instance, in the Gaussian case, you can determine the asymptotic. You can because you know the distribution of the eigenvalue. The eigenvalues, of course, are the singular value of the matrix A. So this is related to this distribution of the singular values. There is a general philosophy that asymptotically log-concave distribution behave like if coordinate would be independent. So you will wait that all the log-concave ensemble, this is why I was put this title, enter the general theory of random matrices. In random matrices, all coordinates are independent. So if you look to such a statement, it tells you that lambda 1 is larger than 1 minus c square root of n divided by n, and is less than 1 plus c square root of n divided by n. In random matrix theory, this is called Bayes' theorem. This is true for any matrix with only with independent entries with 4 moments, with the 4th moment. The largest eigenvalue converge almost surely, and the convergence is very precise. This is square because I'm working with maybe with, yes, these are not the singular value, but the square of the singular value. And this converges to 1 over square root beta, where beta is this ratio. So it is up to constant. Okay, this is a kind of a quantitative version of the Bayes' theorem. questions. What are the asymptotic constants here? Do you have an asymptotic theorem for the eigenvalues in the log-concave ensemble? Same question, for instance, other question of the similar order. The norm of A is less than C plus square root with high probability. This follows easily from this statement here, because you have you just multiply by the n here. You have square root of n plus square root of n. This was, by the way, open question for some time. This solved this question. But question: what about what is the asymptotic? It should be a theorem which is the same as for the Gaussian case, probably, because in some sense, asymptotically, the entries should behave independently. This is why we think that there is something like this. So there are many questions which are going in the direction of in this direction. I should stop here.